Hello everyone, welcome to CAE for you. In this video, we will see about bolt joint analysis. We will start with the basic understanding of the bolted joint, and then we will move on to the FEA simulation covering the pre-processing, solving and the post-processing. To start with, as a basic functionality, we expect the bolt joint to hold two or more parts together, and thereby they act as an integral part. This is very much required when you expect that the parts needs to be dismantled occasionally, and you may need to replace or repair any of the other sub parts. In some of the applications, containing pressure becomes vital, and for example IC engines or pressure vessels, you also have bolted joints where they are used to contain the pressure. Let us look at a typical bolt joint. We have the bolt, top flange, bottom flange and the nut. Here the top and bottom flange represents the parts that are held together, and bolt and nuts acts as the clamping members. So this is typically in the assembled condition, that is just before you start tightening the nut. In order to see how the joint behaves under tightening, we will consider the left picture, which is just the assembled condition, that is just before the tightening, and in the right we have the joint which is fully tightened. The tightening happens by torquing the nut. In the process, we see that the flanges gets compressed, the bolt shank actually gets stretched, but in FEA this could be slightly counterintuitive, which we will touch upon in the later stage. Due to the tightening, the parts which are held together develop contact pressure. As we pointed out, the contact pressure develops between the interfaces. The pressure zone actually determines the effective stiffness. In most of the conditions it could be very complex, however they can be approximated so that rough hand calculations can be performed for design purposes. Now the bolt joint is said to be preloaded or pre-tensioned. It is because as the nut gets torqued, the shank actually experiences the stretching. This tensile load is induced due to the tightening of the bolt. So let us see what happens when the external load gets applied. We have the assembled condition at the leftmost side. In the middle we have the fully tightened condition, and in the right we have the externally loaded condition. As the external load increases, it tends to separate the joint, thereby increases the tension in the shank further. However, the contact pressure between the joints gets relaxed, that is the contact pressure between the parts that are held together previously. Now let us see how the typical bolt joint response looks for an external load. It can be pictorially visualized as shown. The horizontal axis represents the applied load or the external load, and also the various components of the load sharing is shown in the graph. The solid line represents the load shared by the bolt. As you can see, initially the bolt is subjected to the preload, and as the external load increases till certain extent, the load doesn't increase significantly, or the bolt doesn't experience a significant increase in load, but after certain portion the bolt experiences a sudden increase in load. That point is said to be where it loses the complete preload, because of which the load path changes and the bolt experiences a significantly higher load than when it was preloaded. Now, one of the advantage what we can see here is till the bolt joint is preloaded, if there is any variation in the applied load, that is any variation in the applied load, the variation in the bolt load is significantly lesser, which means the alternating component of the fatigue load experienced by the bolt can be significantly less, or it can be significantly reduced by proper preloading. That is one of the major advantage of bolt joint, and this also gives a clear picture of what would be the maximum load capacity of the given bolt joint. Now let us set the simulation objective. We would like to calculate the load carrying capacity of the bolted joint, and we also want to see the stress developed in various components, and what is the contact pressure distribution between the interfaces. This is important to determine whether leakage can be imminent or not. So, by doing this simulation, it would be possible to determine the structural integrity of the bolted joint and also check if there is a possibility of pressure leakage. The end objective of this simulation would be to find the size of the bolts, how many bolts needs to be used, what is the appropriate tightening torque, thereby how much is the preload that it will be requiring, and what is the suitable material. For doing the FEA analysis, we need to do some simplifying assumptions. We assume that the threads are strong enough to withstand the shear stresses that is induced by the external loading and also during the tightening process, and there is sufficient clearance between the shank and the flange hole, or the part that are connected together. This is to ensure that the shank does not interfere with the flanges when the external load is applied. We will be using multiple softwares to perform this simulation. The CAD geometry was created using FreeCad version 0.20. Mesh generation was created using Salome version 9.7, and also we have used a mesh conversion utility UNV to CCX, so that we will be able to convert the mesh generated from Salome to the native mesh format of Calculix. The loading and boundary conditions are defined in Calculix. We will use Calculix CCX for solving. Post processing is done in Calculix and subsequently done using simple spreadsheet program. For our case, we have used Librecalc. Let's move on to CAD modeling. The geometry for this analysis was created using FreeCAD. The geometry consists of three parts: top flange, bottom flange, and the bolt. Let us look into the dimensions of the top flange. For better visibility, I will hide bolt and bottom flange. The top flange was created as a simple extrusion of 30 mm length, which means the flange thickness will be 30 mm. The outer diameter of the flange is 120 mm and the hole diameter is 20 mm. The bottom flange has the same dimensions as that of the top flange, except that it is flipped with respect to the bottom surface of the top flange. Let us look into the dimensions of the bolt. Again, for better visibility, I will hide bottom flange and the top flange. The bolt has been made as a simple revolution. The shank radius is 9 millimeters, which means the diameter will be 18 mm. So there will be a clearance between the bolt shank and the hole, and it is assumed that the shank does not interact with the flanges, so there won't be any contact pairs that will be created between them. The contact will be created only between the bolt surface and the flange surfaces. And another important observation can be made here, that the bolt has been made as an integral part of the shank, which means the thread has enough shear strength to withstand the external load which the joint will experience. Another important point is all the parts should be made as an individual component, so that the contact pairs between them can be created in subsequent pre-processing. This can be done by creating each component as a separate bodies using this create body option, and it can be exported using the export option. You have to select all this at once and you have to export. You can export it into any neutral file format. Here I have exported it as a step geometry, that is in the step format. While you are exporting as a step format, it is important that in the preferences, in import export step option, the scheme is selected as higher than AP203, that is it can be AP214 or AP242, so that the exported geometry will be an assembly rather than a common part. This is very important and essential, as previously mentioned, to create the contact pairs so that the bolted joint can be simulated. I have already exported this geometry, so let us move on for the meshing using Salome. Salome platform is used for meshing as well as slicing the model to generate hex mesh. There is no strict rule that only hex mesh has to be used, while tet mesh also will do the job. Due to the hardware limitations, hex mesh was chosen for better accuracy and faster convergence with lower node count. Due to the length of the video, we will not go through step-by-step explanation. However, we will focus on some of the important aspects to be taken care while preparing the mesh. The imported geometry in Salome should be checked for dimensional consistency. Then you can scale the model as required. Here the model has been already scaled up. Once the model has been imported, the model has to be exploded as comp solid so that we get individual surfaces for applying loads, boundary conditions and defining contact surfaces. The top peripheral surface is used to apply the load. The bottom peripheral surface is used to apply the fixed boundary condition. Contact pairs are generated between the bolt head and the flange head at the top and at the bottom, as well as between the two flange surfaces, that is the bottom and top flange surfaces. While dealing with pretension, Calculix seems to have some limitation in terms of defining the contacts for bodies having pretension. For instance, it is better to keep a small gap between the contact surface of bolt head to the surface where load or boundary conditions are defined. Calculix does not support defining internal surfaces So a separate body has to be created for defining the pretension section. This can be done by simply slicing the bolt geometry and exporting the bottom half or the top half. It is also observed that the mesh refinement near pretension section will also help in getting better results. The mesh sizing are already defined in this case, and we can go ahead with the mesh. We will move on to the mesh module of Salome. You can see the mesh has been already generated, and it is completely pure hex mesh. We are going to use 20 noded hex element in Calculix, so it is necessary to convert the generated mesh to quadratic formulation. In this case, that is also already done, so that option is grayed out here. In case of unstructured mesh, it is good to check the quality of the mesh because poor quality mesh can lead to convergence problem. Salome allows you to check the mesh quality, so that is the option with which you can check the mesh quality. However, we will not check here because it has been already sized properly to generate the good quality mesh. Since everything looks good, we can now export it to UNV format, which will further be converted to .inp format so that Calculix will be able to read the mesh. Let's move on to mesh conversion. The UNV mesh file will be converted using UNV to CCX application. The application takes the UNV file as input and generates the .inp file. It is not a GUI based application. It is simple yet looks a very useful tool. Open the terminal in the location where these files are located so that you don't need to adjust the path. Otherwise, you need to take care of the path so that it works correctly. Once it is open, just type /unv to CCX and the UNV mesh file with its extension. That's it. You can see the mesh file translated to .inp format. Don't forget to remove the line and surface element in the input file to work properly. Now let's prepare the solver deck. Let us walk through the solver deck. We will include the node and element definition, that is from bj.in, and also the surface definitions along with the preload surfaces. The material is steel. We are considering only linear elastic material. Young's modulus and Poisson's ratio are provided here, and we define the solid sections as steel of all the various components. We will use the tie we will tie the surfaces of the nut with the surfaces of the flange, whereas we will use a frictional contact. We will try to use a bonded contact between the bolt head and the flanges, that we will try to mimic it using the tie command, whereas we will use the frictional behavior between the two flanges, that is the top flange and the bottom flange interface. We will define a node to create the preload. and then we will also define the pretension section. Here we will refer the surface that has been created and the reference node which is defined. For this, the axis of or the normal is in z direction, so we use the coordinate 0, 0, 1. We will fix the bottom flange, bottom surface, and we will apply the load on top flange, top surface. Now we will have multiple load steps. The first load step will correspond to the preloading load step, and we will consider 70% of the yield strength of the material. For this example, we will consider that the yield strength is 180 megapascal. The preload will correspond to approximately 32,063 newtons. We will write the displacement and contact details, and also we will try to get the reaction force at the fixed surface, so that we will be able to verify if it matches with the applied external load. Section print of preload surface can also be used to get the preload value that which the bolt experiences. Multiple steps are continued, as we may observe that the load was applied using the point load options, that is, each and every node will get loaded. The load patch contains 680 nodes, so accordingly the load has been divided and the load value has been incremented till the preload. An interesting note here is as the load approaches, or if the load equals the preload, or if the load increases, Calculix will complain and it may not converge. That is not because the bolt joint has lost its load capacity. That is because Calculix suffers convergence if the load is applied in terms of forces. However, if the loads are converted into equivalent displacement and applied, you may experience convergence. We will now run the deck using CCX. The solution is completed. Let us move on to the post processing. It is convenient to load both the input file and the result file, so that individual components can be loaded and the results can be viewed. For instance, let me see the set details, so that the set details are available for loading. Let me load the bolt. I will hide the model edges. You see the orientation fits good. Okay, this looks good. Let's look into the results. We will see the Y displacement. So this is actually as expected, that we see a linear variation of the displacement along the z direction. We will also try to see what is the stress induced. This is in between 122 to 134 megapascals. If we recollect the load applied with the cross sectional area, the expected result is 126 megapascal, and we see that the results are pretty good. Now let us look into the results of other components. Let us look into the stress values. For better visualization, actually we can do a cut. Before that, let me invoke the elements. Takes a while. Here. Let me reorient. So we could clearly see the distribution of the z-axis stress, that is the axial stress, and we also see that the influence of the stress is acting as a truncated cone. We will also try to see how the contact stresses are getting developed. So we could clearly see the pressure fringes as expected. As the external load increases, the contact pressure actually vanishes. Let's see if we can animate this. So we were able to see that as the external load increases, the contact pressure diminishes, which indicates that the joint is actually opening up. So this behavior is actually as expected. So we can say that with Calculix we will be able to do a dependable ball joint simulation. Of course, this is a very simple case. However, a more complicated. However, this methodology can be extended for more complex geometries. However, the objective of this work is to show that Calculix, even though a open source software, is very powerful enough to simulate complicated mechanical behavior, and it can be extended to actual industrial problems with reasonable accuracy. In order to verify if the results are reasonably good and if the Calculix offers more Calculix offers more facilities in order to get Calculix offers flexibility and good post processing options to get some of the critical insights which can help in preparing the bolt characteristic diagram. The results obtained are further post processed using LibreCalc. It can be seen that the bolt joint characteristics can be easily generated using the analysis that we perform using Calculix. Thank you for watching our video.